All right, folks, we are going to do number 34. Let's get started. All right, Heather in her Corvette accelerates at the rate of 3, whatever, while Jill in her Jaguar accelerates at that rate. Okay, they both start from rest and the origin in the of an X and Y. Fuck it. All right, Heather in her Corvette accelerates at the rate of 3, whatever that vector is, meters per second square, while Jill in her Jaguar accelerates at that vector. They both start from rest at the origin of an XY coordinate system after 5 seconds. What is it? Okay. So before I read the question, I'm going to think about what's going on. So Heather and Jill both racing their vehicles at some component. And since we are going to start from the origin, let's put this coordinate system out of the way. So this is going to be the x-axis, this is going to be the y-axis. The acceleration for Heather is going to be 3 meters per second square in the i-hat direction minus 2 meters per second square in the j-hat direction. So that's going to be this component going downward somewhere like this, some vector direction. Now, keep in mind about this problem, folks. This is going to be the component that they're going to accelerate. So if they both accelerate at the same component, at the same acceleration, think about this. What you're basically doing is you're scaling this direction by a factor of the magnitude of a. So after 5 seconds, really, you could just treat this as the angle and that magnitude. Really, it's not, it's kind of like or do it however you guys want. All right, so let's draw the vector for Jaguar. Let's put this as a different color. Jaguar accelerates at, what color do we use? Let's use orange, or let's use orange. So the acceleration for Jaguar is going to be 1 meters per second square in the i-hat direction plus 3 meters per second square in the j-hat direction. So that's going to be a vector that's going to be this component right here, somewhere in there. I don't really know. It doesn't matter if I draw them to scale or not. What matters is the mathematics. All right, guys. So after 5 seconds, the velocity, remember that the velocity is going to be the acceleration times the time, presuming that the initial velocity is 0. So the velocity for Heather, once you calculate this, is going to be, what is that? So 1500 meters per second in the i-hat direction minus 10 meters per second in the j-hat direction. So the velocity for Jill is going to be 5 meters per second in the i-hat direction plus 15 meters per second in the j-hat direction. Now the question is asking, what is Heather's speed relative to Jill? So realistically, what the relative speed is we're going to take the velocity of H minus the velocity of Jill. And this should get us into the value at 1495 meters per second in the i-hat direction, minus 25 meters per second in the j-hat direction. It's asking for the speed. So I guess we're going to take the magnitude of this. So the magnitude of that value, and that's going to be part A. So let me put this in my TI-84 calculator. I haven't really calculated this yet. So 95. All right, so that's the answer, folks. I really thought that said 300 meters per second. I don't know how square, but I don't know how. I don't know how I put that, but whatever. Let's move. What I'm going to be doing instead for part B, see, what's part B? How far apart are they? All right, so what I'm going to be doing instead, folks, is I'm going to take the magnitude of Heather. So the magnitude of Heather and the magnitude of Jill. So let's get those values. So that those two magnitude is going to be, I'm going to put it as the square root. So this is going to be the square root of 10 meters per second square. That's the magnitude of Jill. And this is going to be the magnitude of Heather. That's going to be 13 meters per second square. And the reason why I want to do that is because I want to just scale the vector. So since they're going to be pointing in that direction regardless, I'm just going to scale this length by whatever that formula. So in other words, folks, the length of whatever direction z is, that's going to be really just at squared over 2. So I'm just going to put 5 square times this value and then take a half of that. So I'm going to find Heather first. So that's going to be root 13. That's going to be multiplied by 5 square divided by 2. That's going to be the length for, so the position for Heather, or the length for Heather, is going to be whatever that angle is. I'm just going to worry about the magnitude. So the position for Heather is going to be, or the overall length is going to be 45.07 meters. And the position for Jill, for the other one, Jill, is going to be, we're going to do the same thing. We're going to take that, root 10 times 5 squared divided by 2. That's going to be 39.53 meters per second. I mean meters. And there we go. So this is how far each length is. In order to get to the part, I'm going to do a little trick here. All right, folks, since I am way too lazy to redraw this and it's getting late, I decided to just put the loss of cosine. The length of Heather minus the length of Jill is going to be 67.3. And let's see, what's part C? What is Heather's acceleration to respect to Jill? Well, we can find that. So that's going to be 2 meters per second square in the I hat direction, minus 5 meters per second square in the j hat direction. All right, we are done. I'm way too tired.